Welcome to our channel Circuits Analytica. In this video, we will consider series combination of n number of resistors. The network in the figure consists of n number of resistors connected in series. So when same current flows through the components, we can say that the components are connected in series. In this circuit, same current flows through all the n resistors starting from R1 to Rn. So the resistors are denoted as R1, R2, R3 to Rn. Resistor R1 is connected between node A and node B. Resistance R2 is connected between node B and node C. Resistance Rn is connected between node X and node Y, as we can see in the diagram. A voltage source Vs is connected between node A and node Y. And let the loop current is Is, which flows through the components R1, R2, R3 to Rn. So now let us find voltage drop across each component. So applying Ohm's law, we can find voltage across resistance R1. VR1 is equal to Is into R1. Similarly, VR2 is equal to Is into R2. Vrn is equal to Is into Rn. Now we are going to apply KVL to this loop. So the current is assumed as flowing in the clockwise direction. Considering first voltage term, as we are going from positive potential to negative potential, the voltage drop across resistance R1 should be taken as negative, should be considered as negative. Similar is the case with the other n-1 number of voltages. VR2 is also taken as negative. VR3, VR4, etc. Vrn. All these n terms are taken as negative. And the voltage source Vs should be considered as positive, as the clockwise current flows through Vs from negative potential to positive potential. So when voltage drop across resistors are considered, these terms must be taken as negative, as explained in the previous slide. And when voltage source Vs is considered, that must be taken as positive, as we are going from negative potential to positive potential. Now writing the loop equation. Considering first term, voltage drop across resistance R1 minus VR1 minus VR2 minus VR3 etc. minus Vrn plus Vs is equal to 0. Rearranging the terms, we can write Vs minus VR1 minus VR2 minus etc. minus Vrn is equal to 0. So Vs minus of inside bracket VR1 plus VR2 plus VR3 plus etc. plus Vrn is equal to 0. That means Vs is equal to VR1 plus VR2 plus etc. plus VRN. So this is the application of Kirchhoff's voltage law. So according to Ohm's law, we can write VR1 is equal to IS into R1. VR2 is equal to IS into R2. Similarly, VRN is equal to IS into Rn. Therefore, we can write Vs is equal to Is into R1 plus Is into R2 plus etc. plus Is into Rn. So here Is is a common term in the right hand side. So taking Is outside, we can rewrite this equation as Vs is equal to Is into inside bracket R1 plus R2 plus R3 plus etc. plus Rn. Equation number 1. Now let us consider a loop which consists of just two elements, voltage source Vs and resistance Rs. Current flow through resistance Rs is denoted as Is. According to Ohm's law, we will get Vs is equal to Is into Rs. Equation number 2. Now we have two equations, equation 1 and equation 2. If you look at these two equations, we will find that the left hand side of these two equations are same. That means we can equate these two equations. So equating equation 1 and equation 2, we will get Is into Rs is equal to Is into R1 plus R2 plus R3 plus etc. plus Rn. So cancelling Is from both sides, we will get Rs is equal to R1 plus R2 plus R3 plus etc. plus Rn. Equation number 3. Now let us consider a loop with n number of resistors of same value are connected in series. When n number of resistors of same value are connected in series, then the resultant value is equal to sum of n number of resistors of value R. That means effective value of the series combination is Rs is equal to n times R. So Rs is equal to n into R. Thanks for watching Circuits Analytica. Enjoy learning.